Okay, for the first one, they say selling eggs that are contaminated with salmonella can cause food poisoning in consumers. A large egg producer randomly selects 200 eggs from all the eggs shipped in one day. Okay, the laboratory reports that 9 of these eggs had salmonella contamination. Identify the population, the parameter, the sample, and the statistic. Okay, I think for me, the identifying the sample and the statistic first makes more sense. Those are kind of the easier ones to see, at least for me. So, the sample is just the particular things that were selected. The 200 eggs. So this is the 200 eggs from all the eggs shipped in a certain day. Um, yeah. Okay, so we'll just say the 200 eggs that were selected. Okay, the statistic is in this case, they say the laboratory reports 9 of these eggs had salmonella contamination. So, they said 9 out of the 200 had salmonella poisoning, so that's like a proportion. So, since this is a statistic, a proportion will be p hat. Okay, and this is just 9 out of the 200. Okay, so that's our statistic, which is a sample proportion. All right, and then now it makes sense to do the population. Population is wherever, all the individuals that had a chance of being selected in the sample. So in this case, it's the all the eggs that are shipped on that day. Okay, and then the parameter is just the and this the statistic was the proportion of contaminated eggs. And I should say that also p hat the proportion of contaminated eggs from the sample. Okay, and then the parameter is the true proportion of contaminated eggs in the population. The actual. That were shipped on that particular day. Okay. Yeah, so it makes sense for me to think of what's the sample first. That's usually pretty obvious. And then the population are just all the individuals that could have been selected for the sample. Um, yeah, and then it'll be a little different for everyone. Okay, for the next one, they say an author's written 5 children's books. The number of pages in these books are 64, 66, 71, 73, and 76. Okay, for A, they want us to just list all 10 simple random samples of size n equals 3. Calculate the median number of pages for each sample and display the sampling distribution of the sample median on a dot plot. Okay, so we're just going to group these into groups of 3, these 5 numbers into groups of 3, and then for each group we'll look at the median, and then those 10 medians from each of those groups we'll put on a dot plot. So let's do that first. So there's 64, 66, and 71. And the median, I'll kind of put off to the side, is 66, just the one in the middle. Okay, next one I'll do 64. Whoops. 64, 66, and the next one, 73. Median still 66. 64, 66, 76, still 66. Okay, so we'll just keep going with this. Okay, those are all the ones that start with 64, 66. So I'll do 64 and 71. 73. So, whoops. Okay, 71's the median of that. 4. Okay, 71. Okay, that was 64 and 71, so now we'll do 64, 73, and 76, and that median is 73. Okay, so those are all the ones that involve 64. So now we'll go on to the next one, 66. Okay, you can do 66. Okay, 71 and 73. 71's the median, 66. 6, still 71, and then we could do 66, 73, 76. Okay, that median 73. Okay, and then the last one, we could do 71, 73, 6. Okay. Okay, so let me grab this dot plot. We'll do a dot plot for these. Okay, so I'll put wait, 1, 2, 8. Okay, I'll make this 69 and 70. Okay, 66 is as low as it goes, so we'll stop there. Okay, so there were 3 at 66. There were 4 at 71. And there were 3 at 73. Okay. Alright, so that's for A. So part B, describe how the variability of sampling size distributions of the sampling distribution of sample median would change if the sample size was increased to n equals 4. Okay, so this is the sampling distribution for size 3, right? So there's just 3 in each group, 3 in each sample. And there, this is all possible combinations of 3, so that's what a sampling distribution is. All possible samples of a certain size. So this is a sampling distribution from this population of size n equals 3. So now they want us to say what happens if it was groups of 4. Okay, for B. If it was groups of 4, how would the variability change from this one? So definitely, so as sample size increases, variability decreases. So if the sample size increased to n equals 4, we would expect for the variability to decrease. Okay, so for part C, they say construct the sampling distribution of the sample median for samples of size n equals 4. Okay, does the sampling distribution support your answer to part B? Explain your reason. So they want us to do the same thing we did for A, but when you look at groups of 4, samples of group of size 4, and then C, we'll do a dot plot and let's see if it's obvious whether the variability decreases or not, or even just see if it decreases. Okay, so we'll do groups of 4 now. Okay, the median, since there's an even amount, it'll be the average of the middle two. Okay, so the average of those is 68.5. Okay, there's only going to be 5 of these, so it'll be pretty small. Okay, and you can kind of think of it as each group will just be leaving out 1. So we left out 76 for this one. Now I'll leave out 73 maybe. Leave out 73 and then get 76. Okay, so the average of those is same thing. Okay, next one. Leave out 71. Okay, the average of those is 69.5. Okay, next one. Okay, we'll leave out 66. Okay, the average of middle two is 72. And then we'll leave out the first one, 64. Okay, and average 72. Okay, so here's a dot plot that we'll use for this one. So we'll do 68 and a half, 68 and a half, 69 and a half, and then two 72s. Okay, so the average of each one looks to be about 70. Somewhere around 70 it looks like if you took the average of all these, or if you took the average of all these, it's about 70. So you can see these are definitely more spread out from 70 than these are. These are packed towards the middle. So this confirms that the variability for the larger sample size that we took, so for the sampling distribution, the variability is definitely less than the sampling distribution for n equals 3. I'll put this is n equals 4 sampling distribution. and this was the n equals 3, 1. Okay, so sample size increased here, the variability decreased. Okay, researchers in Norway analyzed data on the birth weights of 400,000 newborns over a 6-year period. The distribution of birth weights is approximately normal with a mean of 3,668 grams and a standard deviation of 511 grams. Okay, sketch a graph that displays the distribution of birth weights for this population. Okay, so they say it's approximately normal, so we know it's going to be some kind of normal curve. So we'll put, they give us the mean is 3,668, so we'll just put that in our graph in the middle. 3,668. Okay, and then besides that, we want to, they give us the standard deviation is 511, so probably it's a good idea to list values that are certain, whole number standard deviations away from this. So just add 511 to this a couple times, and we'll get different standard deviations away from this mean. Okay, so if you add 511 to 3,668, you get 4179. So here I'll make, this will be this one, and then this next one is 4179. Okay, this one 2 away. So that's one standard deviation above the mean. If we add 511 to that, we get 4690. And then, maybe we'll do one more standard deviation. So this will be 3 standard deviations of the mean. So just add 511 to the 4690, and you get 5201. Okay, so that's 3 standard deviations above the mean. So now we'll go below the mean by subtracting 511. So if you subtract 511 from 3668, you get 3157. Subtract 511 from that, you get 2646. And then maybe one more, subtract 511 from that, we get 2135. Okay, so there's just listing the mean, and then this is 1 standard deviation above the mean, 2 standard deviations above the mean, 3 standard deviations above the mean, and that's probably good. Okay, and then besides that, just draw a normal curve, kind of just showing that it's normal. The peak should be at the mean somewhere. We don't know how high it goes, but okay, so just something like that. Doesn't have to be perfect. Okay, so next one, they say sketch for B, part B. Sketch a possible graph of the distribution of birth weights for a simple random sample of size 5. So they just want us to pretend like we took a simple random sample of size 5, and what's a possible value of those 5 birth weights. So, who knows? Probably more will be around the average. And so here I'll use these same values from above. So here, this is 3668. If that's the middle, maybe a couple came from around here. They'll be close to the middle, maybe a couple close together. And who knows, maybe an outlier happened somewhere. Okay. Alright, so that's it. Calculate, and they say calculate the range for this sample. Okay, so let's say this one here. So range is biggest minus smallest. Let's say that one, we'll just estimate that as like 4,700. And then this one here, we'll estimate it, we'll say 3,000. Okay, so the range for this sample would be 4,700 minus 3,000, which equals 1,700. Okay. Okay, next thing for part C. They say, or after part B actually. So they say in this population of birth weights, 300 and, in this population, the range, maximum minus minimum of birth weights is 3,417 grams. Okay, we use technology to take 500 simple random samples of size n equals 5 and calculated the range, max minus min, for each sample. The dot plot shows the results here. Okay, so part C. In the graph provided, there's a dot at approximately 2,800. So I think they're referring to this dot here. Explain what this value represents. Okay, so for part C. So that 2,800, that represents out of the 500 simple random samples, which is really simulated, from some software. One of those samples, one of the 500 samples, had a range of 2,800, and that's what that dot represents. So this dot represents one of the 500 simple random samples that had a range of 2,800. Okay, so last one, part D. Is the sample range an unbiased estimator of the population range? Give evidence from the graph to support your answer. Okay, so definitely not an unbiased estimator. From what I've read, you don't say it's a biased estimator, you just say it's not unbiased. So an unbiased estimator would be a value that from your sample that is the same as the population. Okay, so here they say in this population the range is 3,417. So for us, the mean should be the same, but it's not. Right, we can see, yeah, really for this, the population range was 3,417 grams. We can see this, if you look at all these sample ranges, if the sample range was an unbiased estimator of the population range, then in this dot plot of simulated sample ranges, the mean should be the same as the population. But we can see the mean here, I don't know, maybe it looks like around 1,200 or so. The mean range of birth weights for each sample is about 1,200 in all these samples. But if it was an unbiased estimator, it would be 3,417. Okay, so we'll say, okay, is the sample range an unbiased estimator? No. Sample range is not an unbiased estimator. Because the mean of the simulated sample range this is from the dot plot is not equal to and was really much lower than 3417, which is the range of the population, something like that. Okay, so just saying, if you take all these all these ranges of 500 different samples, the average, the mean of these is about 1,200. So if it was an unbiased estimator, then we could say, oh, the mean of all the ranges of all the samples is the same as the actual population range, but that's obviously not true, and that's really never true for ranges. Ranges will never be unbiased estimators because you're never going to have, range from a population is whatever the range is. That's the largest possible range that you could possibly get. So it's not going to be an average. The largest thing that you could possibly get won't be an average of all these different samples. It's all, the samples are always going to be at most equal to, but mostly less than. So okay, so the Gallup poll asked a random sample of 1,540 adults, do you happen to jog? Suppose that the true proportion of all adults who jog is p equals 0.15. Okay, what's the mean of the sampling distribution of p hat? Okay, so the mean of the sampling distribution of p hat is going to be the same as the true proportion, which is of the population, which they say to assume is 0.15, or suppose. Yeah, they're saying that's, I guess, the claim. So that's the mean of our sampling distribution. Okay, calculate and interpret the standard deviation of the sampling distribution. Of p hat. Check that the 10% condition is met. Okay, now so the standard deviation of the sampling distribution for p hat. So we're just going to use that formula. So formula here, I'll write the formula first. It's p times 1 minus p over n. Okay, so p is, they tell us is 0.15. 1 minus p is 0.85. And then our sample size was 1,540. Okay, and this ends up being about 0.0091, we'll say. Okay, and then they say check that the 10% condition is met, so definitely 10% condition is met. The 10% condition, which is the same thing as the 10% rule. Condition is met because the sample of 1,540 adults is less than number of all adults, number of adults. Okay. Okay, part C. Is the sampling distribution of p hat approximately normal? Justify your answer. Um, yeah, so it'll definitely be approximately normal. So if we look at law of large counts, so if we look at n times p and n times 1 minus p. Okay, so n times p, there was, lowercase n is the sample size, so that's 1540. And then our p they give us is 0.15. Okay, if we do that, that ends up being 231. Okay, so this is greater than or equal to 10. Okay, and then n 1540 times 1 minus p, 0.85. Okay, this ends up being 1309. Okay, that's greater than or equal to 10. Okay, then we can say by the law of large counts, the sampling distribution p hat is approximately normal. Okay. Not much room. Okay, and then the last one they say find the probability that between 13% and 17% of people jog in a random sample of 1,540 adults. Okay, so this is just a matter of using the calculator. Anytime they say find the probability and you're dealing with a normal distribution, if they say find the probability, greater than something, less than something, or between two values, or really just any kind of range of values, we'll use normal CDF. Okay, so let's do that quick. I'll just kind of put it here over all this stuff. I'll move it in a second. Okay, so doing normal CDF. So do second vars. Go to number 2. Okay, so our lower is going to be the 0.13. They want to know the probability that it's between 13% and then 17%. We know the true proportion is 15%, 0.15, and then we calculated the standard deviation before was that 0.0091. Okay, and that's it, and then just hit enter one more time, and then that's it. So 0.972 part D. I'll just put probability, not much room to write, equals 0.972. Okay, and that should make sense because the standard deviation is about 0.01, and so 13% is about 0.02 away from this, and 17% about 0.02 away from this. So these values are about 2 standard deviations away from the mean, and remember, 2 standard deviations, that the amount of data is 95%, and it's a little bit more than 2 standard deviations. these values, so it makes sense this should be a little bit more than 95%. So, okay, so they say thousands of travelers pass through the airport in Guadalajara, Mexico each day. Before leaving the airport, each passenger must pass through the customs inspection area. Customs agents want to be sure that passengers do not bring illegal items into the country, but they do not have time to search every traveler's luggage. Instead, they require each person to press a button. Either a red or green bulb lights up. If the red light flashes, the passenger will be searched by customs agents. If a green light means go ahead. Customs agents claim that 30% of all travelers will be stopped, get a red light, because the light has a probability 0.3 of showing red on any push of the button. To test this claim, a concerned citizen watches a random sample of 100 travelers push the button. Only 20 get a red light. Okay, assume that the customs agent's claim is true. So assume that the red light goes off 30% of the time. Okay, find the probability that the proportion of travelers who get a red light in a random sample of 100 travelers is less than or equal to the result in this sample. So less than or equal to 0.2. Okay, so they asked for a probability. So we know we're gonna, and this is gonna be a normal curve, because one thing, what do they say? So they say the sample is 100 travelers, which is definitely less than 10% of all travelers. So we can assume that this is approximately normal, and then we can use normal CDF to find the probability. Okay, so we want to, maybe we'll first just state what everything is. Actually, we'll state, we know that the lower is just going to be some kind of negative infinity kind of thing, and then the upper is going to be 0.2, which is 20 out of, so let's list all these. So the sample proportion out of that sample, so p hat, was the 20 travelers that got stopped out of the 100 that were observed. That's 0.2. The claim is that the true population, or the true proportion, is 0.3. Okay, and then so we're going to use that as our mean when we do normal CDF, and then now we just have to try to find the standard deviation of our sampling proportion, sampling distribution. So this will be square root. Okay, and then when we do this, we'll use the claimed proportion, which was 0.3, and then 1 minus p. So this is p times 1 minus p over n. And that ends up being 0.0458. Okay, so now we have everything that we really need for the calculator. Let's just plug this in. Okay, I'll do that here. Okay, so normal CDF. Okay, lower, we'll leave that. Could be negative 1,000, or that's negative 10 to the 99, 10 to the negative 99. 10 to 99, yeah, so upper is 0.2 because we want to see what's the probability that's that or more extreme, which is less. Our average was 0.3, and then our standard deviation was the 0.0458. Let's hit enter, and that's our probability. let's write that here. So, whoops, put that down here for now. Okay, find the probability. So probability is 0.0145. Oops. Okay, so based on your results in Part A, is there convincing evidence that less than 30% of all travelers will be stopped? Explain your reasoning. Okay, so there is convincing evidence. Hold on. Okay, yeah, so there is convincing evidence since, here, let's do, we'll write this out. Okay, since, so the probability was 0.0145, and that's less than 0.05, 5%. There is convincing evidence. And it's against the claim. The claim is that 30% of all travelers will be stopped. So there's convincing evidence, and we got a value that was less than that in our sample, much less. So there's convincing evidence that the true proportion of travelers that gets stopped. There is convincing evidence that the true portion of travelers that gets stopped is less than 30%. Less than 0.3, let's say. Okay. Okay, the Wechsler, let's say, Adult Intelligence Scale, WAIS, is a common IQ test for adults. The distribution of WAIS scores for persons over 16 years of age is approximately normal, with mean 100 and standard deviation 15. Okay, what's the probability that a randomly chosen individual has a WAIS score of 105 or greater? Okay, so this is from what we did last semester. Just they have some normal distribution, and we want to find the probability. Okay, so we can just go right to normal CDF in the calculator. Okay, let's do that here. So we want to know if it's probability that it's 105 or greater. So 105 is the lowest. Upper, you could do 1,000, I don't know, 10,000, something like that. They tell us the mean is 100 of this distribution. And then they tell us that the standard deviation is 15. So this is not a sampling distribution. This is just a normal probability distribution. Okay, so that'll be our probability. So for A, what's the probability? Probability is 0.369. Okay, part B. Find the mean and standard deviation. So here, of the sampling distribution of the average WAIS score, X bar, for a simple random sample of 60 people. Okay, verify the 10% condition is met. Interpret the standard deviation. Okay, so the mean of a sampling distribution for x bar, sampling the mean with 60 people. So we'll do the mean of x bar is going to be just the same as the mean of the population, and they said that that's 100. Okay, and then the standard deviation of this sampling distribution for means. So this is means now, not proportions. So if when you're dealing with proportions, you'll do the square root of p times 1 minus p over n. But for this, we'll take the population standard deviation and divide it by the square root of n. Okay, so they say that's 15 divided by the square root of 60. And that ends up being 1.9365. Okay, so they say verify that the 10% condition is met and interpret the standard deviation. Okay, so this 60, they say, sorry. Yeah, so the sample size was 60. And so this is definitely less than 10, or yeah, less than 10% of the population of all persons over 16 years of age. So I'll say 10% condition met because sample of 60 is less than 10% of all persons over 16 years of age. Okay, and that's where this sample came from. Okay, and then interpret the standard deviation. Okay, so that's one thing. So next thing, so yeah. Okay, so we'll say to interpret this, the mean, what was it, WAIS score sample of 60 adults. Okay, the mean score for a random sample of 60 adults typically varies by 1.9365. There's no units to this. Yeah, so it varies by that. From a mean of 100. Okay, so something like that. Okay, part C, do that here. What's the probability that the average WAIS score of a simple random sample of 60 people is 105 or greater? Okay, so we've already calculated the, we already said the mean and calculated the standard deviation for sampling distribution where n is 60. So now we'll just do normal CDF in a calculator. Okay, so we'll do normal CDF. Okay, lower and upper still the same because we want to know now just from this sample what's the probability that it's greater than 105. So mean will stay the same. So really the only thing that's changing is the standard deviation. And that is whatever, yeah, 0.1 or 1.9365, yeah. Okay, and that's it. So 0.005, we'll say. Put that up here. Okay, so probability 0.005. Okay, part D. So would your answers to any of parts A, B, or C be effective if the distribution of WAIS scores in the adult population was distinctly not normal? Okay, so they're asking us kind of like that central limit theorem type question, or at least for one of the parts. So we'll go for part A. So, we did, to calculate this probability for part A, we were assuming it was normal. We did normal CDF, which assumes that the population is normal. If the population wasn't normal and we did everything the same, we did normal CDF, then yeah, who knows? Depends on how not normal the actual scores were. But yeah, we would expect to get a different answer for part A. For part B, what was it? Yeah, part B was just finding mean and standard deviation of the sampling distribution, and that just depends on, the mean is the same as the mean of the population, as long as the 10% condition is met, which it was. So that wouldn't change, even if the population wasn't normal, like they said, since the 10% condition met and the sample size is big enough, that won't be affected. So standard deviation would stay the same, and the mean would stay the same. For part C, what's the probability that the average WAIS score of 60 people is 105 or greater? Okay, so we know, since the sample size was bigger than 30 by the central limit theorem, that means that no matter what the shape of the population was, since the sample size is greater than or equal to 30, our sampling distribution is going to be normal. So when we use normal CDF to find this probability, we would get this same thing no matter what, the same probability no matter what the shape of the population was. So okay, I'm not going to write that. There's not that much room. So okay, so last one. The gypsy moth is a serious threat to oak and aspen trees. The state agriculture department places traps throughout the state to detect the moths. Each month, a simple random sample of 50 traps is inspected. The number of moths in each trap is recorded, and the mean number of moths is calculated. Okay, based on years of data, the distribution of moth counts is discrete and strongly skewed, with a mean of 0.5 and a standard deviation of 0.7. Okay, so now we're doing a problem where the population is not normal, right? They say strongly skewed. So let's see. Okay, explain why it's reasonable to use a normal distribution to approximate the sampling distribution of X bar for simple random samples of size 50. Okay. Really, it's just a simple sense our sample size of 50 is greater than or equal to 30 by the central limit theorem. Okay, the sampling distribution of sample means will be approximately normal. Okay, something like that. Okay, B, estimate the probability that the mean number of moths in a sample size of 50 is greater than or equal to 0.6. Okay, so we kind of already established that our sampling distribution of sample means will be approximately normal, so we can use normal CDF. So I'm going to go right to the calculator. And yeah, just go right to normal CDF. And just see that we can, the only thing that's going to be, that we need to calculate is the standard deviation. Okay, so we want to know probability it's greater than 0.6. So we'll just leave the upper like that. Our mean was 0.5. And then we can calculate the standard deviation. So the standard deviation that they said was 0.7, and we can just divide it by the square root of the sample size, and we can do it right in there. If they don't ask for what's the standard deviation, we can just put it right in there, and that'll be the exact value anyways. Okay, so that's it. So that's the probability. That the mean number of moths in a sample size of 50 is greater than or equal to 0.6. Okay, I'll just leave that there. Probability, and we'll round it to the nearest thousandths as always. So 0.156. Okay, so for part C, actually maybe I'll put this here. Okay, part C. In a recent month, the mean number of moths in a certain simple random sample of size 50 was 0.6. Based on this result, is there convincing evidence that the moth population is getting larger in this state? Okay, so the mean number of moths in a sample size 50 was 0.6. That was greater than the claimed mean, or than the than the mean that was based on years of data. So is there convincing? Yeah, so there will not be convincing evidence. Not convincing evidence. That the moth population is getting larger. In this state. Because the probability of getting a sample mean of 0.6 or greater of a sample of 50 is 0.156, which is greater than 0.05, which is 5%. So yeah, what did I say? There's not convincing evidence that the moth population is getting larger in this state because the probability of getting a sample mean of 0.6 or greater from a sample size of 50 is 0.156 greater than 0.05. Okay, and that's perfect. Okay, so that's it. So yeah, bigger than 0.05, not convincing evidence against the claim. Less than 0.05, there is convincing evidence against the claim.